In this video, we are going to go over section 4.1. Section 4.1 deals with using the first derivative to graph the function. So the goal of this section is to use the first derivative and analyze the graph. And then also within the first derivative, we can use that to graph the original function. So there are a couple things to go over in this section. First, concept is increasing and decreasing function. So on a certain interval a to b, if the first derivative is positive value, then the original function is increasing, and then vice versa. If the first derivative is a negative value, then the original graph is a decreasing. Critical value. What is a critical value? If you have a derivative equal to 0, so this is when derivative is positive, and this is when the derivative is negative, and this is when the derivative is exactly 0, then we call that critical value. Okay, so two possible way that you can have a critical value: when the function is a 0, when the first derivative is 0, or the first derivative does not exist. Then those two are the critical points. Procedure. So how do we use first derivative to find the local extrema value? Let C be the value of critical value of f, which means those are the points where the derivative is equal to 0 or the derivative does not exist. Construct a sign chart for f prime close to or on either side of C, the critical value. Local minimum, if first derivative change from negative to positive. We call this local maximum. The critical value is a local maximum if the derivative change from positive to negative. Neither a local mean nor local max if f prime does not change sign. So we will use this procedure to analyze the graph of f of x. So let's do a couple warm-up problems, and then we'll get to the whole entire procedure part. So here we have f of x, 21 all over x plus 3. They want you to find the derivative. They want you to find the critical value, and they want you to partition the number for the first derivative. So let's start with finding the derivative. So part A, you see that this is a quotient, so I'm going to be applying the quotient rule to take the derivative. So it's low d high derivative of numerator, which is 0, minus high derivative of low, x plus 3 is just 1, all over low square. So I have 0 minus 21, so negative 21 over x plus 3 whole thing square is my f prime of x. So that's part A. Part B, let's find the critical value. Now for critical value, there are two definitions where the critical value exists. When the derivative is equal to 0, and then when the derivative does not exist. So there are two cases. So f prime of 0 or f prime does not exist. So think about this. When you have a function that is a fraction, when do we have a fraction equal to 0? That's when the numerator equal to 0. And because numerator is negative 21, you can never have f prime equal to 0. You're never going to have the numerator 0. So this one, we don't have anything. So so first cases is negative 21 over x plus 3 square. When is it 0? Never. So this case, we cannot find any critical value. So let's check for the second case. When do we have our derivative function does not exist. That's when the denominator equals 0, because fraction have a undefined value when the denominator equals 0. So in this situation, second case, we do have a critical value. So that's when, let me note, negative 21 x plus 3 squared does not exist when denominator is equal to 0. So let's find that out. To get rid of the square, I would square root. So I have x plus 3 equals 0. Subtract 3, so I have x equal negative 3. So we only have one critical value, which is at negative 3. Now let's just double check. We got that, but is x negative 3 in our domain of f? Well, actually, if you look at our domain of f, going back to the domain of original function, domain is everything except negative 3. So even though we got our value, this is not in domain. So we do not have any critical value. There is no critical value. So always check all the definition, find out those critical value, possible critical value, and check and see if your possible critical value is in the domain. If it is, then that's a critical value. If not, that's not a critical value. So partition number for the first derivative. So part C. So that's what we are going to partition them using these critical value. So we can we found these possible critical values, so negative 3, and that wasn't our critical value, so that's pretty much it. Okay, so let me write a note. Partition numbers are found by setting the first derivative equal to 0, which in this case can happen for our example. And then so these two are the number that we use to partition the number line. So this one we did not have any value, and then where it is undefined, which we have it here, x equals negative 3 is undefined. So your number line should have just partition at negative 3. The whole number line can be separated into two parts, before negative 3, after negative 3. So there's a slight different term, critical value. When we partition these numbers using prime, f prime equals 0, or f prime does not exist, those are my partition numbers. And then critical value is if this partition number is in the domain or not. Okay, so don't get confused between the two terms. Critical value has to be within the domain of a f. Partition number is any value that makes the derivative 0 or f prime does not exist. We will be using this partitioning number to look at where function is increasing, decreasing, and to find the local mean, local max. So that will be kind of like for the next exercise. So let's take a look at number 2. So number 2, we have f of x is equal to 3x to the 4th plus 4x cubed minus a. Part A, find the interval on which function is increasing, part B, where function is decreasing, and then find the local extrema. So let's go back to our definition. Now, f of x is increasing when derivative value is greater than 0. F of x is decreasing when the derivative value is less than 0. So I'm going to be taking the derivative of our original function. And then look where the derivative is positive and where the derivative is negative. So if I take the derivative, this is power rule, term by term. So 4 comes down, so 12x cubed plus 12x squared. And then the last term disappear. Okay. And we want to know, this means f prime of x is greater than 0. And then this is when f prime of x is less than 0. So we want to kind of look at where it's equal to 0. And then look and see if that value is greater than 0 or less than 0. So let's find the critical value. So I'm going to set it equal to 0 or f prime does not exist. Now this is a polynomial, no fraction, so there will be no critical value coming from the second situation. So I'm only going to set it equal to 0 and solve for x. So 12x cubed plus 12x squared, set it equal to 0. They both have a common factor, which is 12x squared. So I have x plus 1 equal to 0. So we have two ways, 12x squared equals 0, x plus 1 equals 0. So one of the answer is when x equals 0. And then the next one is when x equals -1. So these are my partitioning number. So I'm going to be using my number line to partition the number, indicate -1 and then 0. This is where f prime is exactly equal to 0, right? Right there. This is when, same thing here. This is when, so this part I'll do it f prime. This is when the prime equal to 0 and then also the prime equal to 0. Now we want to know where the prime, f prime is positive and where it's negative. So this is how you find out. You have 3 intervals to consider. This part here, between -infinity to -1. And then you have -1 to 0 and then 0 to infinity. So I'm going to use test number from all 3 regions. So test number, I'll say 1, 2, 3. For region 1, test number, I'm going to use -2. Now, when you pick a test number, you can pick any number between in this area. So you don't have to use -2. You can use -10. You can use -5 as long as it's not -1. So anything smaller than -1 works. So what's a good test point for number 2? Any number between -1 to 0. So I'll pick -0.5. So for number 2 region, I'm going to use test number x equal -0.5. And then number 3, any number greater than 0 on a number line. So I'll use really easy number 1. Okay, so we literally plug it in into a prime function here. Our prime function is this because we want to know where the prime function is 0 or positive or negative. So let's plug it into this one here. So I'm going to have f prime of -2, so that will be 12 times negative 2 cube plus 12 times negative 2 square. So f prime of negative 2, I have 12, that's a negative 8, plus 12 times 4. So f prime of negative 2 is negative 96 plus 48. So we get negative 48. So I'm getting a negative value for the first region. Okay. And then let's try negative half. So f prime of negative half, 12 times negative half cube plus 12 times negative half square. So if we continue, that's 12 times negative 1 over 8, 12 times 1 over 4. So I get, I can reduce 4 goes here twice, 3 times, so negative 3 over 2. And then this one, whole number 3. So my final answer, I get 3 over 2, positive 3 over 2. So this time, I'm getting positive number. So I'll say this is a positive. And then let's test the last region using test number 1. So f prime, don't plug it into original. You're always plug it into the first derivative function to look at where it's increasing. So f prime of 1 is 12, 1 cube plus 12, 1 square. So that's 12 plus 12, which is 24. We get a positive again. So this will be positive. Okay. Now, so what does that mean? That means here, my region over here, this means our original function, because you have a derivative negative, original function will be decreasing. My original function will be increasing and then also increasing in this region. So my final answer, I'll put it in an interval. So increasing is these two regions, and we are not including 0 because 0 is not positive. It's actually, this is where the derivative is exactly 0. Those are my critical value. So we exclude that. So my final answer is going to be negative 1 all the way up to 0, union with 0 to infinity. So that will be part A answer. Part B will be negative, so actually let's just put it over here like this. So that will be part A. Part B answer will be decreasing only from negative infinity to 0. Okay. And then part C, what is local extrema? How do we find the local extrema? Local extrema is either local mean or local max. So we have, when f prime change from negative to positive, we get local minimum. When f prime changes from positive to negative sign, we have a maximum. And then if it doesn't change any sign, that point, that critical value is neither mean or max. So do we have a sign change? So over here, let me move this one a little bit down. We have a sign change. We get at this critical value, we do have a sign change, negative to positive. So we have some kind of function going decreasing to increasing. So this is a local mean, because we get from negative to positive, negative to positive. Now here, this critical value is neither mean nor max because we have positive to positive. There's no sign change. So this critical value is neither one. So part C, final answer, we do have local extrema, just one, which is at x equal -1. So because there's a sign change, so x equal -1 is a local mean. And then to find the actual point, we are gonna take f equal to -1, plug it into the original function and find out where that value is. Because local extrema is a point, so I need an order pair. So 3 times -1 to the 4th power plus 4 to the -1 cube minus 8. So I'm gonna have 3 minus 4 minus 8. So I'm going to have -9. So we do have a local minimum point at -1 comma -9. Okay? So that's how we use derivative function to get information of our original function. Now here, because this is a first example, I'm going to double check with my graphing calculator to make sure that A, B, C is matching, okay? I can graph this original function and actually get all this information, but we are using a derivative to get that information. So let's check. So pulling out my graphing calculator, so let's set it as 3x raised to the 4th power plus 4x, let's type it one more time, 3x raised to the 4th plus 4x raised to the 3rd power minus 8. And then I'll just change to the original standard window. And this is kind of like what's happening here. So double checking this point over here. You can kind of trace it over here. I'll just do it over here. Captured it, and let me open up and then double check. Okay. Now, take a look at this one over here, right? We have our function, right? Decreasing. So these are my decreasing part, right? So let's check. It should decrease. Oh, this part is decreasing, right? Because it's going the graph is decreasing. And then it's going, so this part is, the graph is decreasing because it's getting smaller, and then it's increasing and then increasing again. So we do have a decreasing, increasing, and then increasing. Let's check. This point is about, and you can do it more accurately, but this point right over here do seem like at -1, good, because it's between -3 to 0. And then this point over here that was right at 0, you can see that this there are critical value here and here. So we have a negative, positive, and positive. So that's good. And then this point, we call that this was a local mean. And then we do have that local minimum here. That's the smallest. That's the lowest point of the graph. Is it a -1 comma -9? Let's quickly check. So if I trace and then put -1, I should have -9 right there. So that's good. So it does match everything. So we can use the first derivative to get a sense of what the graph look like. Okay. So I'm going to also let's erase. Oh. Okay. So I'll leave it over here. Okay. I want it to move, but if I start moving, I'm not grabbing any points, but so I'll just leave it here so you can reference. All right, let's do one more problem. This time we're gonna add one more concept. We are going to actually sketch the graph. Here we didn't sketch it, but with all this information, we are going to create a graph that looks like this one over here, okay? So we need all the information that we need. So I'm going to take the first derivative and look at where it's increasing, decreasing, find the critical value, and then use those ones to sketch the graph. So let's begin with where it's increasing, decreasing. So f prime of x, that will be 6x squared plus 6x minus 12. Let's set it equal to 0. And then f prime of x does not exist. This one, we do not have to consider it because polynomial is existing everywhere. It's not a fraction. So 6x squared plus 6x minus 12, set it equal to 0. Common GCF of 6x squared plus x minus 2. So I have 6 times x plus 2, x minus 1. So I have two places, set it each factor equal to 0. You know that 6 is never equal to 0. So only two places where x equal negative 2 and then x equal 1. And these are all within the domain here because domain of our original polynomial is all real. So let's use our critical value to partition our number line. Okay. So we have negative 2, positive 1, and this will be my f prime, and then this will be my f section. So there are again 3 regions. So region 1, region 2, region 3. So for region 1, I'm gonna use test number x equal negative 3 because that's fits between negative infinity to negative 2. So the second part, I would use a 0 because that's the easy number. So second region, my test number is x equals 0. And I will use test number as positive 2 for region 3. And remember, we are plugging in back to the derivative function because increasing means when the derivative is positive, decreasing means when the derivative value is negative. So let's plug it in those numbers into our derivative function, which is right over here. This is our derivative function. So you have f prime of negative 3, 6 times negative 3 squared plus 6 times negative 3 minus 12. I have 54 minus 18 minus 12. So final answer, I get positive 24. So I have a positive here. Plug it in 0 into our derivative function. So that will be 6 times 0 squared plus 6 times 0 minus 12. So this will be negative 12. So I have a negative. If I use test number positive 2, I'm going to have 6 times 2 squared plus 6 times 2 minus 12. So I'm going to have a 24 plus 12 minus 12. I get positive 24. So we have increasing, decreasing, and then increasing. Let's look at, so those are my part. So to answer the first question, part A, my increasing will be region negative infinity to negative 2, not included. Do not include negative 2 because that's actually when the derivative function is a 0. union with, there's a second part, positive 1 to positive infinity. Decreasing only between -2 to -1. So it didn't ask for this one, so we can also notate extrema, local extrema. I have an increasing, decreasing, so that's a local max, highest point on the graph. And then this one is at certain interval. Decreasing to increasing, so this is a local mean. So we do have this time both local max and local mean. Let's use these information to kind of give a quick sketch, okay? And then it's important to find where local mean and local max points are to get the accurate graph, just like here. So I'm going to actually find where the local minimum point and local maximum is. Now to find that, we plug it in back to the original, right? To get that number. So let's do that. So f -2, if I plug it back to the original one, I have 2 times -2 cube plus 3 times -2 square minus 12 times -2. So if I plug it in everything, I'm going to have, so 2, let me use a calculator, 2 cube plus 3 times -2 square minus 12 times -2. I get positive 20. So my local max point is at -2, 20. F prime of positive 1, that's 2 times -12, -2 cube plus 3. 1 cube plus 3 times 1 square minus 12 times 1. So that is 2 plus 3 minus 12, which is 5, minus 12, which is at -7. So I'm going to have local mean point at 1, -7. Okay, so let's sketch our graph, part C, using the information. I'm gonna indicate these 2 points, which is negative, let me even make it a little bit bigger. So positive 1, -7, 1, 2, 3, 4, 5, 6, 7. And then you have -2, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's count by 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So somewhere here. And then I have to change this one too because we are counting by 2s. So -2, -4, -6, so -7 is somewhere here. So we have a anything from negative to positive up to -2. So that's all the way up to here. So kind of like imagine having this kind of like over here, partitioning, right? So I should have a positive. So an increasing function. So I have all, and then this -2, and then 1 is where it's 0. So I have kind of like increasing going on, and then hit that point, and then I have a actually Negative 2 is at, that's not the 0. Negative 2 is critical value, that's not 0. I should erase this one too. That's the derivative is 0. So you have some kind of like increasing. So I need to somehow pass where the x-intercept. I don't know where that yet. And then I have to have between negative 2 to 1, I should have a decreasing function. So kind of like decreasing and then increasing. Something like this. Okay. So I should have something very similar looking like this when I actually graph it. So if I graph this one, I'll do that with the calculator. Let's just double check how accurate our graph looks like. We have 2x cubed plus 3 x squared minus 12x. Okay, and this is I should have y like 25, something like this, right? And that looks pretty